Hi, I am Paola Andrea URBANO. I'm presenting this conference titled Simulation and Optimization of Control Strategy for Renewable Energy Low Power Systems. Contents: Introduction, Methodology, Results, Annexes, Conclusions, and References. Let's start. Introduction. A simulation is an approximate imitation of a process or system that represents its operation over the time. Optimization is an act, process, or methodology of making something as perfect, functional, or effective as possible. Control strategy or dispatch strategy is a set of rules governing how the system charges the battery bank on a hybrid renewable energy system, HRES. Renewable energy system, HRES, is a set of equipment and devices which generates electric power to supply determined electric flow, transforming the energy from renewable sources. The systems, low power, are between 10 and 100 kilowatts. An energy system which uses more than one energy sources is a hybrid system. For example, wind, photovoltaics. We have here wind power and photovoltaics. Control strategies for energy dispatch, HOMER. Note following. The generation technologies produces only enough power to serve the load and does not charge the battery bank. In the cycle charge, the generation technologies operates at its maximum rated capacity to fulfill the demand requirements and charge the battery bank with the excess. Allows to establish a set point of the state of charge between 0 and 100 in a way that if batteries are under this set point, the generator has been, and if the generator has been working during the last hour, it will charge the battery bank to achieve the set point. Figure 3 shows the window displayed by HOMER to select the control strategy and the set point, if needed. Inverter controller modes. We are presenting the operation modes available in some converters. For example, Outback Mate 2, Santrex XW Series, Trace SW Series 2 manufacturers. Those modes of operation are drop use, high battery transfer, grid use, generator starts, and float mode. Drop disconnects the AC input source, but will allow it to be reconnected if the low battery could offset point occurs or if the inverter controller is overloaded. Use, connect the inverter to an AC input source. High battery transfer allows to control the use of the grid power based on the set point of the battery voltages and times. A user can maximize renewable energy power through careful HVX usage. It is used with grid-connected inverters that have utility powers as their AC input. It's also used in applications that have enough renewable energy power production to meet the needs of the loads most of the time. It allows the effects to connect to an AC source if battery voltage has fallen below the set point for a time. Grid use allows programming the times that the system connects to an AC input source and enables the use mode. The time and date must be accurately programmed to function properly for weekdays and weekends. It starts the generator, AGS mode. It starts the generator or generators once the conditions are true and will stop the generator only when all the conditions are false, except during a programmed quiet time, normally at night, when noisy generator would be disturbing. The float mode. When a charge controller finishes a bulk charge and moves into the float charge, the mate or inverter controllers directs any other charge controllers into a float charge as well. Related works. Since 90s decade, many researchers related with HRES design, the control strategies, and its influence in the system performance have been published as follows. Mera designed a wind PV hybrid system to light and pumping water in a remote area in Ecuador. LASTRES developed a detailed study of a standalone wind power system with hydrogen storage for a Cuban mountain town. This study allowed to have an actual vision of the economic and technical perspective for these applications in similar conditions in developing countries. Tufo Lopez developed a methodology and software named HOGA to design and optimize hybrid renewable energy systems, taking as a variable the control strategy using genetic algorithms. Hernández designed an integrated energy system with wind hydrogen fuel cell, taking among the many variables and design restrictions the environmental component to evaluate the best systems configuration applying multi-criteria methodologies. Paola review for different configuration of standalone and grid-connected hybrid systems to ensure and finally conclude that the energy management strategies that work well for same-time renewable energy systems may not be the best for other configurations. And now we have the problem here. To solve this problem, we have made this methodology. Methodology and equipment. The project stages begins with first, identification of the components of the hybrid system, such as the energy transformation technologies, solar panel and wind turbine, the storage battery bank, the backup system, in this case is the network, and the demand that is going to be supplied. Number 2, obtaining all the information regarding the storage system for technical sheets and manuals. Number 3, the databases of the load and of an anemometric or meteorological station close to the installed system to estimate the wind and solar resources available. Number 4, take the data from the initial HRES configuration or setting, such as maximums, minimums, values, and set points in general, compared with the default ones. Number 5, verify that meteorological energy consumption and system behavior are keeping in records in order to evaluate the system behavior before and after the optimization. Number 6, establish an analogy between modifiable parameters in the simulator and modifiable parameters in the real system configuration. Number 7, obtain the simulation of the current behavior of the system from the initial parameters and the databases of previous years. Number 8, sensitivity analysis around the variable or variables that allow modifying the energy dispatch in the hybrid system and its optimization. Number 9, obtain the value of the evaluated variable that improves the energy performance of the system and enter this information in the configuration of the real system. Number 10, observe the behavior of the real system after modifying the optimization values found by means of the sensitivity analysis. Present the results to the system administrator in order to keep these new settings or return those to the initial values. Now we can see in the figure number 4 a scheme of the HRES located in the Istmo in the Tehuantepec Isthmus. The red lines represent DC bus, the blue ones represent the AC bus. In the pictures we can see the equipment, solar panel with 4 modules, the converter, AC-DC and DC-AC, and all the inputs and outputs of the energy system are all concentrated here. 1 wind turbine and the battery bank composed by 8 batteries connected in series. Continue with the equipment. We can see in figure 5 the HRES control panel, where the main controller allows the configuration of different parameters that are not in self strategies of controls and dispatch of energy. However, the user can maximize the use of renewable energy and minimize supply from the grid through a careful use of parameters and modes of operation. In the figure 6 is the real system human-machine interface, where we could see the grid, the inverters, the loads, and in the left side, and in the right side, the panels, charger controller, and batteries. The figure 7 shows the mismo HRES simulation system, where the AC and DC buses are connected by the converter and the inputs and outputs of the system. As we can see, the real system does not have the wind turbine because it was out of service along the time we were taking the measures. We were expecting to work with the wind turbine, but it was not possible. In the simulation to obtain the optimization, we did not have into account the wind turbine. Configuration before. It is necessary to make an analogy between the charge voltage of the batteries and the state of charge. Since the simulator only uses this one and the inverter only allows the voltage parameter. Most recent inverters models allows to configure either the load voltage or the state of charge. Control strategies analogy. Load following and drop mode. When it comes into operation, the backup system, in this case the network, covers the energy demand. Do not charge the battery bank unless the voltage is lower than the lower limit of protection or lowest voltage put out. Cycle of charge use mode. The backup system, the network, operates to meet the demand and that is not reached to cover with the energy from the renewable sources, and in addition, it charges the batteries until it states of charge set point or flotation voltage. In the table, we can see the analogic parameters values. It was established that the 100% of the state of charge is equivalent to 57.6 volts and the 0% is equivalent to 42 volts. The real behavior of the voltage and the state of charge is not linear, but we took this way as an approximation. The float set point is 71.8 volts, and this is the value to optimize. Results. In the figures 8 and 9, we can note that the real load profile on weekends, it is between 1,710 watt-hours and 513 watt-hours, and on weekends about 215 watt-hours. In the figure 10A and B, we can see the average daily profile and the annual daily profile. In the figure 11 and 12, we can note the daily and the annual wind speed. It is between 3.4 and 4.5 meters per second. Simulation outputs. In the figure 13, it is presented the solar radiation with an average of 5.48 kilowatts-hours by square meter by day. In the figure 14 to 17, we have the annual energy performance of the simulated system. In the figure 14, the bars represent the amount of energy produced. The fraction in yellow is the PV generation, the green is the wind generation, and the purple is the fraction of energy that the grid supports. In figure 15, the lines represent the amount of energy generated along the year, and the black colors mean that the wind was not enough to generate power. In the same way, for the 16 for the solar energy, and in the 17 for the battery bank energy output. Sensitivity analysis. The figure 18 represents the state of charge versus the MPC behavior. The 50% of the state of charge yields better economic results of the lower net present cost, but it is not since it is not convenient to have a battery with a low charge. As we can see in the upper table, the strategy chosen is the cycle of charge. In the lower table, we can see that the state of charge of the 60% has a lower MPC than the one in 71%, the actual value, and a similar value for the operating cost of the system. Results on the real hybrid system. The optimized configuration were implemented in the system with the floating mode off and the drop network operation mode on, with a V-float set point of 51.4 volts, equivalent to the 60% of the state of charge. In this order, in order to have the system operating similarly to an isolated system without connection to the electrical network, where the backup power source is the network itself, just for this academic application. As we can see in the table, annual operating cost was reduced in 0.05%, the net present cost, in 0.02%, the cost of energy, in a 0.08%, and in the other side, the renewable fraction increased in 6.67%. As we can see in the table, and in this last slide, in figures 2 and 3, the energy required from the net was reduced in a 99.76%, and the sales to the net increased from 0 to 25.9%. I'm sorry, the sales to the net increased from 0 to 25.9 kilowatt hours day. Conclusions. The methodology developed is based on HRES operational analysis and the energy performance analysis and the optimization of economic variables, using a logical algorithm that seeks to minimize the cost of the energy produced, varying the control parameters such as the state of charge of batteries and the strategies of control and dispatch of energy. Applying the methodology, it was possible to establish that an adequate energy management for the studied hybrid system is the strategy of the battery charge cycle with a set point of the state of charge of 60% equal to 51.4 volts configured in the float voltage of the inverter. It was possible to reduce energy purchase from the grid to 0.023%, reducing the energy costs to meet the demand that is not covered by the renewable energy. HRES should have a study and optimization process for a better use of renewable resources. Each system is different according to its components, types of energy demand, and the available resources. Performance obtained by simulation is annual operating cost was reduced by 0.05%, the total net present cost was reduced by 0.02%, the cost of energy production was reduced by 0.08%, and the fraction of renewable energy increased from 30 to 32%. Now we have here the references used in this research and the acknowledgement. Authors would like to express our sincere gratitude to the UNICACH Cier, the UNISMO, the Universidad Popular de la Chontalpa, and the CONACYT for its continued supporting during this study. To our dear Dr. Liliana Chavarria Difo, to Mr. Andrew Welch, Technical Advisor in whatplot.com, and to the Quinto Ciermi for giving us this space to share. Thanks. I have 1 minute left, and I just want to dedicate it for a silence moment for all the COVID-19 victims to rest in peace, and their families to have the strength to heal their hearts. Thanks again. If you have any questions, I will be looking forward to answer them. Have a nice day. Bye.